All right, let's talk about training a neural network. It can seem pretty complex, right? But it's also a really fascinating process. We're going to peel back the layers and really dig into how these incredibly powerful models actually learn.
So, how does an AI model really learn anything? I'll tell you, it's definitely not magic. It's actually a super methodical process of, well, navigating towards the best possible answer. Imagine you're on an expedition. You have a clear goal, a destination you need to reach, but the map you're using, it's incredibly treacherous.
That journey is all about finding one single point, the absolute lowest point in this huge invisible landscape. In the biz, we call this landscape the loss function. It's basically just a fancy mathematical way of measuring how wrong the model's predictions are. The higher the landscape, the more wrong it is. So our entire goal, our whole mission is to find the absolute bottom, that one spot where the model makes the fewest mistakes.
But here's the thing, that journey is absolutely full of traps. The more complex your model gets, the more wild and convoluted this landscape becomes. And there are two massive challenges, two major traps that can completely stop our model dead in its tracks. So let's talk about that first big challenge, the optimization itself. It's all about charting this unseen terrain. And trust me, for a deep neural network, this landscape is a minefield of hidden traps. Okay, so one of the biggest traps is the local minimum. Imagine our little navigator finding a valley. It looks around and every direction is uphill. So it thinks, great, I've reached the bottom, job done. But what it doesn't realize is that it's just stuck in a small ditch. The real destination, the deepest canyon in the entire landscape, that's the global minimum, is somewhere else entirely. Getting stuck here means you've settled for a pretty mediocre solution when a much, much better one was out there. And the other huge trap? It's called overfitting. This is where the model gets a little too smart for its own good. It doesn't just learn the path, it memorizes every single pebble, every crack in the pavement of the training data. It even memorizes all the random noise. So it looks like a genius on the data it's already seen, but the second you give it a new, slightly different path, it's completely lost. It never learned the actual map, just one specific route. It failed to generalize. So how does our navigator even move? What's the engine powering this whole journey? Well, it all starts with a foundational, but really powerful, concept called gradient descent. So how does this work? It's actually beautifully simple. At any point on the landscape, the model asks one question: which way is steepest? That direction is called the gradient. But remember, we want to go down, not up. So it just takes a small step in the exact opposite direction. Then it stops, looks around again, finds the new steepest downhill direction, and takes another step. Lather, rinse, repeat. Over and over, each little step adjusts the model's internal knobs, its weights, getting it closer and closer to that sweet spot of minimum error. Now, doing this on the entire dataset for every single step is super accurate, but for modern datasets, it's just way too slow. It's computationally a nightmare. So we've got some clever variations. First up is stochastic gradient descent, or SGD. This one's wild. It just grabs one random data point to calculate the next step. It's incredibly fast, and all that randomness can actually help it bounce out of those pesky local minima. The downside? Well, it's noisy and can bounce around a lot. Then you have the happy medium, many-batch gradient descent. This is the one most people use. It takes a small, manageable chunk of data for each step. You get a great balance of speed from SGD and stability from the full batch version. It's really the best of both worlds. Okay, so basic gradient descent is our trusty engine, but let's be honest, it can be a bit slow. It's time for an upgrade. We're going to look at how we can soak up this engine to make our navigator smarter, faster, and way more efficient. The first big upgrade is called momentum, and the name is perfect. Think about a ball rolling down a hill. Once it gets going, it builds up momentum, right? It doesn't just stop at every tiny little bump in the road. That's exactly what this does for our optimizer. It adds a fraction of the last step's direction to the current step. This gives it inertia, helping it to just cruise right past those small, annoying local minima and keep heading confidently in the right general direction. Next up, we've got RMS prop. If momentum is about inertia, think of RMS prop as a high-tech adaptive suspension system. It looks at the recent terrain it's been on. If the road has been really steep and bumpy in one direction, it slows down, taking smaller, more careful steps. But if it's on a long, flat, straight section, it speeds up and takes bigger strides. This adaptive learning rate is a game changer because it stops the whole process from getting stuck or flying off a cliff. And that brings us to the king of optimizers, ADAM. The name stands for Adaptive Moment Estimation, and it's brilliant because it's not an either-or. It literally combines the best of both worlds. It takes the downhill momentum we just talked about and pairs it with the adaptive learning rates from RMS Prop. The result? An incredibly robust, powerful, and efficient optimizer that just works. It works so well on so many different problems that, honestly, it's become the default go-to choice for almost everyone training a neural network today.
All right, so we've got a supercharged engine now. Our navigator is fast. But a fast car without brakes or steering is just a recipe for disaster. We need guardrails to keep it from flying off the road into that overfitting trap we talked about earlier.
The main way we install these guardrails is with something called regularization. Basically, we add a penalty for complexity. We tell the model, hey, I don't want you to get too complicated. L1 regularization does this by pushing a lot of the model's internal weights all the way to 0, effectively simplifying the model by turning off parts of it. L2 is a bit gentler. It just discourages any single weight from getting too big and having too much influence. And then there's data augmentation, which is a super clever trick. We just create fake data. We take our training images and rotate them, flip them, change the colors, teaching the model what a cat looks like from all angles, not just one specific photo. Now, this next one is one of my favorites. It's called Dropout, and it's a pretty kind of crazy idea. Imagine your neural network is a team of experts working on a problem. Dropout comes in, and for every single training step, randomly tells some of the team members to just take a break, sit this one out. This forces the remaining team members to get better at their jobs individually, because they can't get lazy and just rely on their friends to do the work. It prevents them from becoming too dependent on each other. And we're not talking about a small number here. A dropout rate of 50% is totally common. Think about that. For any given update, half of your network might just be turned off. It sounds insane, but it works wonders. Of course, when it's time to actually make a prediction, you bring the whole team back, but you adjust their influence to account for the chaotic training they went through. Another absolutely crucial guardrail is batch normalization. So inside a deep network, as the first few layers learn and change, the data they pass on to the next layers also changes a lot. It's a problem called internal covariant shift, which is a fancy way of saying each layer is trying to learn on a constantly shifting foundation. It's like trying to navigate while your map keeps changing. Batch normalization fixes this. After every few steps, it basically recenters the map for every single layer, stabilizing the entire learning process and making everything run so much more smoothly. And finally, how you start the journey matters a lot. This is where proper weight initialization comes in. If you start all your model's weights at 0 or just some random crazy numbers, the learning signal can either fizzle out to nothing, the vanishing gradient problem, or blow up completely, the exploding gradient problem. So techniques like Xavier or He initialization give the model a smart, sensible starting point, making sure the journey gets off on the right foot. Okay, so we've spent all this time talking about how to navigate the landscape. But there's a final crucial piece to this whole puzzle. What if we could actually design the landscape itself to make the journey easier? That's what network architecture is all about. Take images, for example. We use convolutional neural networks, or CNNs. They are built on the assumption that pixels near each other are related, so they design a landscape that's specifically shaped to find local patterns, like edges and textures, and then build those up into more complex shapes. The landscape itself is predisposed to solving image problems. Well, what about something like text or a time series, where the order of things is everything? For that, we use recurrent neural networks, RNNs, and their more powerful cousins, LSTMs. These architectures create a landscape where memory is built right in. The shape of the terrain at any given point depends on what came before it, making them perfect for understanding context and sequence in language. And then came transformers. These things completely revolutionized natural language processing. Their secret weapon is a mechanism called self-attention. It allows the model, when looking at a single word, to also pay attention to every other word in the sentence, no matter how far away. This creates an incredibly rich and complex landscape that's amazing at understanding the deep, long-range connections within data. So you see, this journey of optimization is really never over. The tools we've covered, from the basic engine of gradient descent to the powerhouse ADAM optimizer, and the essential guardrails like dropout and batch norm, these are what allow us to navigate the incredible complexity of today's AI. But as we move forward, the really exciting question isn't just about building better navigators. It's about designing entirely new, uncharted landscapes for AI to explore, What will those look like? That's what we get to find out.